Good afternoon, everyone. I'm Yiming Shen from Sun Yat-sen University, and I'm very excited to present our research on automating security dataset construction via LLMs. And this is also a collaboration with researchers from Zhejiang University, Peking University, Monash, PolyU, and UESTC. All right, let's start with some context. Smart contracts are automated scripts typically written in Solidity and deployed on Ethereum. Compared to general-purpose languages like CPP, Java, or Python, this is clearly a low-resource domain, which makes understanding its security risks genuinely difficult. High-quality vulnerability datasets are a key lens for that understanding. But existing dataset construction methods face two core problems. First, manual construction is slow and error-prone. For example, the DAppScan dataset took 44 person-months to build and still carried labeling errors. Second, there is no unified taxonomy. Different datasets use different labeling standards, such as SWC, DASP10, and others. So the same vulnerabilities might be called front-running in one dataset and TOD in another and the block manipulation in a third. That fragmentation makes cross-dataset research and evaluation really painful. To tackle these problems, we apply LLMs to replace the label-intensive parts of dataset construction. We use real-world smart contracts audit reports as our data source, and we adopt CWE, the Common Weakness Enumeration, as a unified taxonomy. CWE is a well-established standard in software security, with a hierarchical structure that covers a wide range of weakness types. This let us automatically build a unified, continuously evolving smart contract vulnerability dataset. Now, applying LLMs to audit reports isn't straightforward. We identify three main challenges. Challenge one is about reports themselves. They are long, complex, and formatted very differently across companies. For example, the Uniswap V4 audit reports is 63 pages long. It mixes critical vulnerability information with legal disclaimers, methodology sections, and lots of other noise. Extracting the right information accurately is no trivial. And challenge two is the scale of CWE. The taxonomy contains over 900 weakness types organized in a complex multi-level tree. Mapping a vulnerability to the right CWE node is not a simple classification task. Challenge 3 is LLM limitations, such as hallucinations, context window constraints, and the well-known lost in middle problem. Combined with the first two challenges, this makes accurate automated labeling genuinely hard. So we build Forge framework. The first is the first end-to-end framework for automatically constructing CWE-labeled smart contract vulnerability datasets from real-world audit reports. The Forge has four modules. The first module is semantic trunker at the left part of the picture. And this trunker passes PDF audit reports and Markdown audit reports and split them into semantically coherent chunks using headings and paragraph boundaries, so each trunk fits within an LLM's context window. The second core module is MapReduce extractor. It processes these trunks in parallel. The map fast extracts project metadata and GitHub repos, commit IDs, and on-chain addresses, as well as vulnerability fields like title, description, and severity. The reduce phase in the second aggregates and deduplicates this into structured JSON output. And for the third classifier, hierarchical classifier, use a tree of thoughts reasoning approach. It's also called TOT, to navigate the CW hierarchy level by level. It uses in-context learning (SAL) to choose the best classification path, and a fallback mechanism ensures that even if it can't reach a leaf node, it returns the closest parent category. Finally, the code fetcher uses the extracted metadata to automatically pull the audited contract source code from GitHub or on-chain block explorers and integrates everything into a complex data entry. Okay, and our evaluation parts covers 4 research questions. AQ1 looks at overall dataset construction effectiveness. AQ2 and AQ3 evaluates extraction and CW classification accuracy. AQ4 assesses the dataset's practical utility. And first, for AQ1, we collected 6,000 about valid audit reports from 47 well-known security firms verified on Etherscan. The resulting dataset contains 81,000 solidity files, with over 59% from version 0.8 and above, and 27,000 vulnerability records, covering 296 CW categories. And the right side shows an example of dataset entry, from project information to vulnerability records, title, description, severity, and location of each vulnerability. Okay, and for AQ2 and AQ3, we used confidence interval-based random sampling, 95% confidence level and 10% confidence interval, giving us 96 samples for manual validation. And AQ2 evaluates forges extraction accuracy across fields like on-chain addresses, URLs, vulnerability description shows before. And the average precision across all categories is 95.6 with a Marco F1 score of 86.1%. And for AQ3, we evaluate the CW classification accuracy, since even expert auditors can disagree on the same vulnerabilities classification, so we use Krippendorf's alpha to measure inter-annotators' agreement, and the resulting alpha is 0.87, which exceeds the commonly accepted reliability threshold of 0.80. This means our LLM-driven classification reaches near expert-level consistency. Okay, for AQ4, we evaluate 13 mainstream smart contract detection tools by mapping each to the detectable vulnerability types to CW categories, then running them against real vulnerabilities in our dataset. The results are striking. The best F1 score is only 80.59%, and the average is just 5% above. Some tools fail to detect any vulnerabilities at all. And this is not only validates Forge's utility as a benchmark, it also exposes a serious gap between existing detection tools and the complexity of real-world vulnerabilities. And after the evaluation, we also doing some empirical study. Moving to the discussion section, we use Forge's large scale to run empirical study of the smart contract security ecosystem. First, we visualize security risks from a CWE perspective, combining vulnerability frequency with CVSS V4 severity scores in a tree map. The color depths represents average severity, and box size represents frequency. The hierarchical containment reflects the CWE's category structure. A few key findings from this picture in the high-level abstract pillar types. The coding practice issues like CWE 710 appear frequently but pose relatively low risk, is shallow color, and they mainly affect maintainability. Meanwhile, low-frequency vulnerabilities like arithmetic exceptions, CW 682, can cause severe damage when they do occur. And access control flaws, CW 284, have the highest average severity at all overall. And okay, then we compared this to what the academic community actually focuses on, using Web3 bug survey in the right side of the table. Our 37 top conference papers as our baseline, we found that researchers heavily studied reentrancy and integer bugs as at the main focused vulnerability. But vulnerabilities like higher real-world severity like communication, channel verification issues, and cryptographic signature problems receive much less attention. We think this gap might have two causes. First, researchers naturally focus on vulnerabilities that are easier to detect technically. And second, existing tools and methods struggle with business logic vulnerabilities that require deep semantic understanding. All right, and then we also compare smart contract security risks to traditional software security, specifically OSOP top 10. Several high severity smart contract risks like reentrancy and arithmetic issues have no equivalent in OSOP. These are directly tied to blockchain specific properties, and because smart contracts are inherently financial, vulnerabilities that would have limited impact in traditional software can cause catastrophic losses here. On the flip side, some traditional security patterns like OSOP's A10 SSRF simply don't apply in a decentralized environment on-chain. And new threat patterns like press manipulation attacks and cross-chain bridge exploits are much more prominent in contract audits. The takeaway is clear. Smart contract security can't just borrow from traditional software security. It needs its own dedicated frameworks to chains and best practices. And okay, finally, a quick note on further work. Following our responsible maintenance commitment outlined in the paper, we have collected new high-quality audit reports from December 2024 through February 2026 based on feedback from early adopters. And with ongoing manual verification, we have releases for curated moderate scale EVM smart contract vulnerability dataset, particularly suited for LLM benchmark evaluation like audit agent benchmark. And the link is on the slide. You can, if you like, you can please give us a star. Thank you. Okay, that's all from me. Thank you so much for listening. I'm very happy to take any questions. You can reach me through email, LinkedIn, and GitHub issues. All right, so see you.